Hey, I think it's the time. Good afternoon. Welcome to lecture 16 of computer architecture course. Today, as promised, we're going to start discussing about flash memory and solid state drives. Yesterday, we discussed about emerging memory technologies and the fact that these technologies are really important to investigate and to do research on them because they can potentially provide orders of magnitude better performance, energy efficiency, better capacity. But of course, they also come with a lot of shortcomings, a lot of challenges. So people have worked on them a lot, and people are working on them to essentially enable adoption of these technologies in computer systems. That doesn't mean that all these technologies that we discussed yesterday and technologies that we didn't discuss because of the interest of the time, they need to, find a way into our computer systems. But in the research, we should still do research and we should still conduct interesting studies because they can potentially provide a lot of interesting insights that can be used in many other works as well. As I said also yesterday, flash memory was also very much emerging, and it was kind of a doubtful technology for at least 2 decades. Many scientists, they were working on flash memory, and they were trying to actually get some kind of funding from different agencies to conduct research on flash memory. And they were actually receiving a lot of pushback from companies, from funding agencies, that essentially this technology is not going anywhere. But they were resilient, and I think we should be thankful of them, because they did research. And the fact that this technology succeed is not random. It's just the fact that many people actually have worked on it and improve it and make it possible such that you can use it and we can use it. So that's why I'm very excited about this lecture. And I think it's very much interestingly aligned with what we started yesterday. We're going to have 2 lectures on flash memory and solid state drives. Today, I will mostly actually go over also flash memory, but then I will also provide some system level, let's say, techniques or architectural techniques when you want to design these solid state drives, because it's kind of a storage subsystem. But next week, hopefully, we're going to also jump into detail of flash memory. And we're going to do similarly what we have done, for example, in DRAM technology, like a lot of studies that we have done to understand the reliability issues of flash memory and how we can overcome these reliability issues. So that part, I think I will leave it for next week. But today we're going to see also a lot about flash memory, how it works, how the read-write operations are happening, and what are the techniques that we can use in order to make this storage subsystem and SSD that essentially we have in our today's systems. Okay, any question? Are you excited enough? I hope I did my best. Okay, let's go. So we have a kind of ambitious agenda. First, we're going to see about overview of SSD organization, how storage controller and request is handling in the SSD. Also, we're going to see about NAND flash hierarchy, NAND flash read and write operations. But then later on, we're going to see a bit more detail about different components of the SSD system, like how we do address mapping, garbage collection, I/O scheduling, and flash memory array parallelism. This part, actually, I/O scheduling, I discussed it a little bit briefly when we were discussing about memory controllers. So this part is going to be actually a bit fast this time because you already know about it, but other parts are kind of relatively new. So modern SSD architecture is a complicated system that consists of multiple cores, hardware controllers, DRAM, and NAND flash memory packages. So this, for example, is a picture of one example modern SSDs, and you can see that in this picture we have 4 NAND packages from this side and also 4 NAND packages the other side of the board, which is not shown here. In total, we have 8 NAND packages or NAND, let's say, chips, you can think of it. And each package actually provides 128 gigabytes. So in total, this SSD actually provides 1 terabyte of space, for example. In addition to that, we have DRAM, which is LPDDR DRAM. So the size of this DRAM is usually 0.1% of the total SSD capacity. And why is that? We're going to see later. But that's more or less the size of this DRAM. And also we have another chip, which is a SSD controller, which essentially in that we have multiple cores, we have hardware flash controllers, and in each flash controller we do request handling, ECC randomization, encryption, and many things. So a lot of actually components are there surrounding all these flash chips to make it work. And that's why we call this system as a storage subsystem, because there are a lot of components working together to make it possible. And when we were discussing about in the memory controller, we say that the controller that we have for flash chips are much more intelligent. Now you can actually have a better sense of it. Like in memory controller, in the processor, we don't really have that many components. That they are trying to control DRAM. But here in SSD, there are a lot of things going on to control how flash chips can work. So if here also provides another view, which again, we have this processor, like storage controller, essentially does a lot of different tasks. One of them is implementing a host interface layer, or HIL. Depending on the interface that you are using, for example, SATA or NVMe, there are some software code that needs to be run in order to such that you obey that interface, right? So that part is actually implemented in this storage controller. And another important function is actually FTL, Flash Translation Layer, which actually does a lot of exciting tasks. One is data cache management. So there is this DRAM here that you can also use it as part of a cache and also write buffer. So managing that actually has been done in this FTL. Also, FTL does is address translation, which we're going to see why we need address translation, and some other operations like garbage collection, word leveling, refreshing, and many more. So FTL actually is the most, I would say, complicated and the most important part of the SSD system. And flash controller does ECC and randomizations, and they essentially control NAND flash packages. Inside the DRAM, we actually keep different data. One is that host request queue. So each request is going to be assigned to a queue, and they're going to be that such that the SSD tries to bring the data which is needed to address that request, fill it up completely in the DRAM, and then reply to the host system. Also, a part of the DRAM is for write buffer. Similarly, we discussed about having a write buffer for PCM yesterday. For similar reasons, also for flash chips, we can also have write buffer. And you also have a table for logical to physical mapping, which we're going to see why. But essentially, you need to have there is a table in that DRAM such that you understand which any logical address is mapped to which physical location, essentially. And at the same time, we also basically store some metadata inside the DRAM for controlling reasons. Like one of them is PE cycles, like number of program and arrays happening on each of these NAND flash blocks, for example. We're going to see more about details of all these things later, but here just providing an overview. So now let's try to have a walkthrough example in the line of, okay, we want to write to the SSD, and how is it work? So when we send a write request, we first have a communication with the host operating system through this HIL, which is so it's going to be implemented. A certain interface can be SATA or NVMe. So a host IO request includes essentially request direction, whether or not you are doing read or write. Also the offset, which is essentially you should know. So from the operating system, the view of the storage is like an array of sectors, right? So it's a flat array of sectors. So you should know on which location you are writing. So that sector is actually kind of conventional name coming from HDDs, if you know about it. Like there we had this sector, and we could read from sector by sector. But still, people also use that definition when they work with SSDs for compatibility reasons, essentially. So we need to inform the SSD about the offset that we want to write or read from it. And also the size, like how many sectors you want to write or how many sectors you want to read. And also the total size of that request should be actually typically aligned by 4 kilobytes. And that's because of the page size that we have, which is usually 4 kilobytes. Then after going through the host request queue, we go through the write buffer. So whenever we send a write request, we go to the write buffer. There is a small difference when you send a write request to the SSD, which you want to be persistent or synchronized. For those requests, you cannot only write them to the write buffer. You need to also wait such that that write happened really in the flash chips, because that you can say that it's persistent. Inside the write buffer, it might not be persistent because it's DRAM, right? However, there is one thing about that DRAM, which SSDs, actually modern SSDs, they provide enough capacitors. So they have some capacitors that these capacitors provide enough charge when power cutoff happens. So when suddenly the power of the SSD just cut because of, I don't know, whatever reason, we have enough capacitors that they can provide enough charge to de-stage that buffer to the flash chips. So in order to make sure that this device is persistent, that's one of the criteria that it has. And that's actually one of the reasons that they cannot make that DRAM buffer large enough. They cannot make it larger and larger, because if they make it larger and larger, they need to add more capacitors as well. And they will come at the price of scalability, essentially. So we buffer usually our write in that write buffer. And this is very important to reduce write latency. Remember about from PCM also, write latency in flash memory is also quite long. So we write to the write buffer so that reduce the latency. And by writing to that buffer also, you are potentially enabling more flexible I/O scheduling, because in general, we have this kind of asymmetric latencies in terms of read and write in flash chips. Reads are relatively faster, like they can be tens to hundreds times faster than writes. So even in that scenario, you really cannot schedule read and write. Most of the time, you really prefer to schedule reads, because they are much faster. However, when you have this write buffer, that can potentially enable you to more such that you can also think about, okay, how flexibly you can schedule read and write inside the modern SSDs. And at the same time, it's also helpful for improving lifetime, because you're hopefully capturing that write or update in the DRAM buffer, and you're not updating the flash chips. But this is not very likely. The problem is that at the storage level, locality is not very much, because that locality has been captured a lot at the caches and then in the DRAM. So when the request actually reaches the storage, there is not much of locality there. So it's very unlikely that you update some pages, and then soon after you update that page again, So it might happen in the future, but not very soon. So you might be lucky and you can capture that in that DRAM, but you might not be also that lucky as well. So the size of that write buffer is limited, as I said, is actually tens of megabytes. It depends on the architecture and the model, but it's not very large. And the main reason, as I said, is about the capacitors, that they need to be there to ensure data integrity, even under sudden power off. Question? Okay. So after that, after data cache management, we go to the address translation. And this part is actually important when you want to write to the flash chips. So if you write to the write buffer and then you're done with it, actually most of the time when we write to the write buffer, we send the acknowledgement to the host. For many cases, we can do that. And that's why we don't really need to immediately go to the address translation part. But when you want to write it to the flash chip, you need to go to the address translation, which is a core functionality for out-of-place writes. So one thing which we're gonna see also later, in flash chips, in flash cell, you cannot update. So when you write, and when you want to write something else, you first need to erase it and then write it. So there's a property which we're gonna see is gonna be clear when we start about that. So that's an erase before write property which we have for flash chips. So now the problem is that when you want to update a page, this page has been stored in a flash, let's say, block that consists of several pages. So when you want to update that potential page, what you need to do, if you want to do in-place write, is that you need to copy everything that has been stored there, which might be hundreds of pages. You need to move them, for example, to a DRAM, internal DRAM, and then you update that specific page inside the DRAM, and you erase the whole block, which is hundreds of pages, and then you write everything back. Okay, so that's the update which could happen inside the flash chip if you want to do it in place updates. And you can guess now that why we don't do in place updates. So in flash chips, we do out of place updates. So whenever you want to update or when you want to exactly write, you just invalidate the original copy of that page and you just write it somewhere else. So that's why the physical address is going to be different time to time. So the logical address which coming from the host can be mapped to different physical location internally inside the SSD. And that's why we need to go through this logical to physical mapping. Is it clear now? Good. So we maintain this L2P mapping. And the mapping granularity is also 4 kilobyte. It can be also 16 kilobyte, depending on the implementation. But modern SSDs, especially also for enterprise SSDs, they are usually using 4 kilobyte mapping granularity. And that's why we are storing 4 bytes for each, assuming that each L2P entry is around 4 bytes. You are storing 4 bytes for each 4 kilobyte of data. And this actually gives you this basically ratio, 0.1% of the total SSD. So that's why I said that usually that DRAM size is 1.1% of the total SSD capacity. Make sense? Okay. So another important operation, which might not be related to that write, but indirectly actually related. So remember that when we write, we do out of place write, right? So at some point you're gonna run out of pages, right? Because you just write somewhere else and then write somewhere else. So at some point you don't have enough available pages that you can write to it. So there is a process which we call it garbage collection that actually runs in the background. Sometimes it might not be on the background and actually can cause some performance overhead. Essentially for your normal operations. We're gonna also see a lot about garbage collection. But essentially garbage collection is to reclaim free pages. So there is a process that garbage collection tries to copy, and we find a victim block, and then move valid pages from that block to some other places, and then erase that block to make enough number of free pages, essentially. We're going to see later about it, but that's the procedure of garbage collection, which can be basically invoked after several writes that we have. Also, varileveling is very important because flash cells, also similar to other emerging memory technologies, they have limited endurance. So it's very important that you level varying of all flash dies, not dies, let's say blocks. So that's why people try to keep the number of, for example, arrays and program arrays. This is why we use this metadata, for example. We keep the number of program arrays for each flash block. And then we try to make sure that we are varying all these blocks in a balanced way. So we don't have a block which is quite hot, you're keep programming and erasing that, or some blocks that they are cold. If that's the case, you might actually migrate some of these blocks. And it's actually is quite easy to implement in flash memory, right? In SSDs, because you can easily remap the logical to another physical location. But this might not be that easy, for example, in DRAM. When you have, for example, this, think about this RowHammer, when you are accessing one row, remapping that row to another location is not that easy, right? Because that procedure of logical to physical location is not implemented that thoroughly inside the DRAM chip. And another important operation is actually the data refreshing, which FTL does that also. So this the data refresh try to refresh pages with long retention ages. So flash memory are considered to be also non-volatile, which they can retain the charge for a long time, maybe forever. But that's too ideal. After some time, you really need to refresh them. Otherwise, you may not be able to read it from them reliably. So we don't need to refresh flash dies or flash chips actually as frequent of DRAM rows, for example, DRAM banks. But you need to do it at some point, like maybe once a month or once a week. As you age your device more and more, you need to refresh it more frequently. And that's also another thing. So if you have a cool disk that you put some data in it like several years ago, and you just pick it up from your somewhere, and then you put it in your laptop, you may not be able to actually get the data. Because after several years, actually, it's very hard. You might still be able, but then it might be very slow as well. Because, yeah, I will talk about it later. Because when it's aged, actually, the reading procedure is going to be much, much slower as well. We're going to see about it later. So in the Vector example for the right, I also try to explain this procedure, garbage collection, where leveling, and data refreshing. But we're going to also see more about them. Any question? Good. So after that, we get to the flash controller. So flash controller, actually, the main procedure is that does this requires signaling to communicate with the flash chip. So that remember about memory controller also, we had to do this analog operation with the DRAM chip to basically send some pulse for different commands. Like this, I'm now sending this activation command, for example. Now I'm sending write column or read column, this operation. So there is this analog operation that you need to do, and that's part of the memory controller. Flash controller also does that. So there has to be some signaling that needs to be happen in order to communicate with the flash chip. And that part, if you want to learn about it, you can actually check data sheets that we have for flash chips. But it might not be also that interesting because in the end, you just need to know it and implement it. Another important operation in flash controller is actually doing ECC and randomization. So ECC, I think you know about it. Whenever we want to write, we do ECC coded. We code our data with some ECC, and that can be used when you are reading back the data to make sure that you can fix the errors. Randomization is we talk also about it in DRAM. There might be some data pattern that they are basically they can maximize the likelihood of getting errors. So there are some worst case patterns. And vendors actually do a lot to understand those worst case patterns. But the problem is that if you don't, so there are some worst case patterns that if those happens, actually you're going to see more errors. So once you have that, actually potentially also there might be some malicious program or malicious users, that they can also cause those problems, use those worst case patterns. So in order to avoid that, there is a unit in the flash controller, which is randomizer, which try to scramble your data that you want to write using a key. And then that randomized data is potentially, hopefully, is not going through those worst case scenarios. So that's a basic function of randomizing. And ECC also, we talk about it. So we're going to see more about ECC when we do read operation. So after this part, essentially flash controller issues NAND flash commands, which is here is the write command. So send the write command, and then after sending the write command, we are sending the data burst, essentially, the amount of data that we want to write to NAND flash package. Yes. So Locality in what sense? Randomizer is just randomizing the data that you want to write, not in the address. Yeah. You're gonna actually, this is gonna be cleared up next week. I mean, in DRAM, I think you can think about it. When you have interference, when you have, like, think about column hammer, all these things that we discussed. When you have more ones, for example, you have more charging and discharging, this can actually potentially affect more interference. Similar things also can be here in flash memory, but we're gonna actually see a little bit more about it next week when we go through data patterns in flash chip that can cause issues. Okay. Yes. Potentially, yes, we do. Yeah. I'm not sure if they do it all the time, but there are some works that they do, and I don't know if it's completely implemented or is always supported. So that I don't know, but potentially, yes, we have that. Yeah. So, I mean, think about it. Like, for example, if you have for example, there is a data pattern that that if that happened in the row, like I don't know, let's say all ones, it's not also one row. There might be several rows, and some combination of data pattern across these rows can actually, for example, cause you, you lose charge faster. Indeed, I'm thinking about retention failure. So some data pattern actually can cause that. So remember that when we wanted to profile retention failures, we had to do that. We discussed about it, right? So if people know about worst case patterns, they can potentially use those also. I mean, they may do it maliciously or not also, but that would cause some errors, the worst case errors, which in the end, ECC is not strong enough to support that. So we want to avoid those cases, which those cases we're gonna put a lot of pressure on ECC and other reliability techniques that we have in the system. So by randomizing, you're reducing the likelihood of those cases, essentially. When you randomize, you potentially are saying that, okay, it's very unlikely that I get to that, pattern. At least I can say that very with high likelihood you don't allow it maliciously. At least people cannot use those patterns on purpose. Say it again. For each page, when you want to write it, you need to randomize your page. Yeah, and then when you're reading back, you need to de-randomize it first. You use the same key to de-randomize, essentially. So it's a kind of a pseudo randomization, which is actually reversible. Good questions. Okay. Now also let's look at the other way. We receive a read. So after going through the HIL, which now we have a read operations, we can first actually check out the cache. That's write buffer, or you can think of it as a data cache management. So you basically, it can be also the case that you are reading from the page that you already written it in the write buffer. So if that's the case, basically we returns the corresponding request immediately with the data. So we don't need to read from flash chips. Yeah, but also think about it that a host read request can be involved with several pages. It might be the case that a few pages of that read request can be handled from that write buffer, but other pages may not. And you need to go through flash chips for those. So in that case, actually, you need to wait. So we wait until we have all the pages, all the requested pages are ready, and then we get back to the host system. And that actually would happen a lot, which in the end limit the effectiveness of having that data cache, essentially. So after that, if we need to access the flash chips, you need to find the address. And that's why we query this logical to physical mapping to understand which exact flash chips, which page, block, and page you need to access. And once you know the exact physical address, you go through this flash controller and access that specific or corresponding NAND flash package. You get the data, and then you need to do performing ECC decoding. So flash controller does this ECC decoding, check if the data is correct, and also do the de-randomizations. So the thing is that it might be the case that ECC decoding fails. So when you do ECC decoding fail, you need to retry the read. And that would cause actually the more longer latency for flash SSD reads. Sometimes for one read, you need to retry it actually several times until you get it correctly. And so that's why when the SSDs are getting aged, or for example, you are accessing a page which has not been updated for a long time, meaning that you didn't refresh it also frequently. I mean, nowadays actually modern SSDs does refreshing. So you may not actually see it a lot, but in the past it wasn't the case. And there might be some pages that you write in your SSD and you don't touch it for a long time. So those pages, when you wanted to access them, actually people show that they are much slower. So the read throughput that you're getting from SSD is much lower when you want to access all data, essentially. And that's the main reason is that you need to retry the read until you get it correctly. Yes. So yeah, so ECC implementation in SSD is a bit more complex compared to DRAM. They are using Reid Solomon, if I'm not mistaken, is a bit more complicated techniques. So it tells you essentially that if ECC fails or not. So there is a way. We are not going into detail of that yet. Yes. Yeah, I don't know about it exactly. We have a paper which we're gonna discuss it next week. That, for example, we say that if you do it every week, for example, you can potentially avoid a lot of retention errors. But I think that period actually needs to be dynamic. And in that paper also we discuss having it dynamically. As your SSD is also getting aged, meaning that program arrays are going higher and higher, then actually you need to do it much faster, much more frequently. No, in DRAM, no, we don't do that because DRAM doesn't age in that sense. Yeah, for another reason. Yeah. Exactly. Because we observe that some rows or some cell can retain charge for longer time. So we have a refresh retention time profile, which we could use it for variable retention, variable refresh technique. But here also, yeah, you can adjust the refresh period based on the program array cycles, for example. Yeah, good question. Yes. Yeah, that logical to physical mapping is actually has been stored in the NAND flash chip. But in order to avoid accessing flash chip for get L2P all the time, we move it to the DRAM. But when we shut the system off, actually needs to be back. And there is a procedure that people update that logical mapping on the line as well. So we don't keep all the updates until the end, right? Yeah, that's one thing. So in modern SSDs for enterprise systems, actually NAND, that DRAM is actually large enough that can keep all the L2P mappings. But in the end, we need to write it back to the flash chips. But in actually mobile SSDs, for example, we don't have that large DRAM. And that's why that DRAM is actually just trying to cache a part of L2P, depending on your access patterns, essentially. There are works in the line of that, DFTL, for example, that they discuss how we can cache FTL and access. Yeah, because otherwise you need to do double access. You do one access to the flash chip to get the FTL, to get the L2P entry. And then based on that, you need to do another access to read. And think about it that each of these access might need to be retried also several times. So it's going to be really inefficient. Yeah. Yes. But by area overhead, because it's just a table. You just change the numbers in that table. Yeah. How? I don't understand. No, I don't. Not complexity. I don't think it would. How do you think it might affect? Because maybe I don't understand your logic here. Oh, okay. Okay. You mean decisioning? Yeah, in DRAM controller, as you add more decisioning to be more intelligent, yeah, that adds complexity. But only changing the metadata in that logical to physical mapping table that wouldn't really add complexity, I guess. Okay. But decisioning, yes. As you complicate your decisioning that you want to do inside the storage controller, that can complicate it. Okay, so now we can get to flash cell. I think it's a record, no? It's already 30 minutes and I'm slide 13, so let's see. And we have 200 slides to go, so. Okay. So flash cell, actually, we discussed about it in the past. So it's actually basically a transistor that in transistor, you have gate, source, and drain. And when you want to turn it on, you need to apply enough voltage between the gate and source to such that you can have this current in the transistor. So the only difference here is that, and that gate source voltage should be higher than threshold voltage, some specified threshold voltage. So in flash cell, we have this floating gate essentially between the gate and the substrate, and this floating gate actually can be used in order to modify the threshold voltage of that transistor. So when you program a flash cell, you apply a high voltage, programming voltage between gate and substrate, like here, for example, 20 volt. And with that, you are actually absorbing or tunneling electrons from the substrate, and you trap them in the floating gate. So that's why actually flash cell is also considered as a charge memory. In the end, you are trapping charge. In DRAM, we are trapping charge in the capacitor, but here we are trapping charge, or we are storing charge in the floating gate. And because of that, so when you program it and you trap electrons here, you essentially cause the voltage of the gate to be negative, which means that you need to apply higher gate source voltage to turn this transistor on. And the threshold voltage actually will be increased. So by programming a flash cell, you're going to have a higher threshold voltage. Then when you want to understand that whether or not you have programmed a flash cell or not, you apply a reference voltage between gate source. And that reference voltage is something between nominal threshold voltage and program threshold voltage. If with that reference voltage, that flash cell has been turned on, that means that you didn't program it. If that flash cell didn't turn on, that means that you have programmed it. Simple, no? And then you can encode these two states as, for example, 1 and 0. So in erase mode, which you didn't program it yet, you can encode it as 1, and in the program way, you can encode it as 0. This is called as SLC programming, single level cell. But you can also apply several reference voltages and do it more accurately. And then you can, for example, encode 2 bits or 3 bits or 4 bits. State-of-the-art SSCs, actually, they are TLC or QLC, that they store 3 to 4 bits per flash cell in order to provide capacity. So that's the programming state and read. And when you want to erase it, you need to essentially push back all these electrons. So you apply a negative charge, high again, quite large voltage, like minus 20 volt, between the gate and substrate, and that will push back all these electrons that they are trapped in the floating gate to the substrate. And if you do it long enough to make sure that you actually move back or push back enough number of electrons, then you will get back to the nominal threshold voltage. However, as you can also imagine now, this procedure is not perfect. So when you do programming, so you trap some electrons, but when you do erasing, you might leave some electrons in the floating gate, or you may actually move more number of electrons, So because if you, when you apply that minus 20 volt voltage, if you keep it for a long time, you might actually cause some electrons that you were not trapping them. Actually, there were electrons there. You just move them also back. And then now you're causing some positive charge here. Okay. And so that's why after each program and erase cycles, your threshold voltage is going to be a bit different, that nominal threshold voltage. And when you program it again, then you move to another position. And when you erase it again, so it's not always perfect. And after some time, you're accumulating errors. Okay. And that accumulation can cause that at some point, your flash chip doesn't work. That's actually one of the main reasons here that after several number of program arrays, the flash chip, the flash cell cannot work. That endurance problem that we have is actually, that's one of the reasons. Makes sense? Okay, so yeah, in flash cell, you can actually do also multi-leveling, as you can imagine. So depending on how much charge we are trapping in the floating gate, you can actually encode it more accurately. Here we are showing the 2 bits. Also, we have retention loss in flash chips, similar to DRAM. So a cell leaks electrons over time. So for example, if this is the cell and we have that much electron or charge in the trap, in the floating gate, after 1 year, we're going to have some, charging loss, but still you are able to read it correctly. But maybe after another year, then you will lose more charge and there's going to be a retention error. And which means that we need to refresh at some point to avoid these retention errors. And also we have limited lifetime. So a cell wears out after some number of PE cycling. So here is, for example, after 1 year, having 1,000 PE cycles, you're going to have this amount of retention error. But after 1 year, while you have 10K PE cycles, you're going to have more retention errors. So essentially, having more PE cycles can basically increase the problem of retention errors, essentially. Okay, question. Now we're going to see a little bit more about how the NAND organization works. I'm going to go quickly over it, and then we're going to take a break. So each of these transistors is a NAND cell, and when you combine, you connect them in a string way. So it's called NAND string. And so you can see it's similar to a NAND gate. Like think about CMOS technology when we add, we series all these NMOS transistors. And that's the terminology. That's the analogy which is coming here also. There is also another way of designing NAND, which we call, not NAND actually, flash, which we call it NOR flash. This NAND flash, it can be also NOR flash. In NOR flash, which you're going to see also a picture of it, I guess, next week, that provides more connectivity. So now the connection is actually very much so limited. Like between all these NAND cells, we have only one connection here to the bit line, right? Which means that it will reduce the bandwidth, or also it will increase the latency when you want to read from a specific NAND flash cell. But in NOR flash, they provide much more connectivity, so it's much faster. But the problem is that NOR flash is less dense. And that's why, because of that density and the performance trade-off, most of this product that we have nowadays is much more NAND flash memory. Okay, so we have this NAND string, and so you're going to have a target cell that you want to read and write to it. In order to make sure that that's your target cell, you need to make sure that other cells don't interfere to your procedure. So that's why people apply VPass, which is large enough to turn those transistors on, whether or not you, regardless of programming or not programming. So that's 6 here, like VPass, which is, for example, 6 volt, is actually is a voltage somewhere here. That whether or not you program or not, it's going to turn on that flash cell. So people apply this VPass to other cells, and only the cell that you want to access it, you're going to apply your reference voltage, essentially. So that's a NAND string. It can be like 128 flash cells that they are serially connected. And then we have the definition of page and block. So a large number of cells operate concurrently. So a page is very similar to also DRAM row. So that's one word line in a horizontal way is actually considered a page, which might be 16 kilobyte, for example, with some amount, some metadata, which you can also add it. And a block is also a combination of several pages. It can be hundreds of basically pages in a block. And also think about it that each word line here, so each cell can be also MLC, can be TLC, for example. So if you are storing, for example, 3 bits per cell, you're essentially storing 3 pages per word line. So that's what people usually say, for example, in NAND flash chips. In SLC, you are storing 1 page per word line, but in other kind of designing, you can store several pages per word line. Okay. So now regarding the pages and block, just to also get it a bit more. So this program arrays is actually unidirectional, as we discussed it also. So you program, you tunnel, you trap electrons, and then you need to erase it. You cannot do program and then also program. So it's just one way. So programming a cell, increasing the cell's threshold voltage, and erasing a cell, decreasing the cell's threshold voltage. Programming page cannot change 0 cell to 1. So that's erase before write properties, which you already discussed it. And that's what people do erase at the block level, because erasing is actually quite slow. And we want to also have a good bandwidth for erasing. So people do it at the block level. And then because of that, doing erase at the block level, that makes in-place write on a page very inefficient. And that's why we are doing out-of-place write in the system. This thing I think is now clear, right? So a large number of blocks that they share the same bit line, you can see. So each of these is a NAND string. And several NAND strings. So here is also our block. You know, all these NAND string that, let me get back to this picture actually. So definition of block, you should consider that basically all these, so all NAND strings, so one row is going to be a page, and the combination of page and vertical, horizontal, and then vertically is going to be a block. But in planes, essentially all these blocks, so there are different blocks in the NAND flash die that they are sharing the same bit lines, okay? So this bit line 0 is actually shared across different NAND strings. So that is called a plane in a NAND flash hierarchy. And so now there should be a control transistor. You can think of it like an isolation transistor, just to control which NAND string is actually connected to a bit line. And that's why people add this string select line, SSL, and also GSL, ground select line. So when one block is actually accessing, you need to turn these two transistors on to make this connection to the bit line, essentially. Okay, those are like a essentially isolation transistor that we also see in other in DRAM, for example. So that's also a definition of plane. And then one NAND flash chip can also have several dies. So there are several planes, like 2 to 4 planes, that they are essentially constructing a die. And interestingly, these planes actually, they are sharing row and column decoders. So that's why we have some parallelism here. As long as the access that you're sending to several planes is the same address, same operation, like you want to do read across different planes, and they are sharing the same offset, you can actually benefit from multiplane operations. But if the address is not aligned, then you cannot benefit from multiplane operations. We're going to see about it more later on. Okay, I think now is a good time to take a 10-minute break this time. And we're going to be back about how programming and reading is happening inside the NAND flash chip. You still hear me? Okay, let's continue. So the thing is that when we program a flash cell, so we don't, when we program a flash page or die flash page, there is not there are several cells, right? And in the end, we're going to see a distribution in the erasing and also programming. Similarly, because of process variation. So essentially, there are some, there is not fixed, essentially, threshold voltage, nominal, and also program. This is going to be a distribution. So that's, I think, you know about it also from other, other memories as well. So some cells are more easily programmed or erased. So in the end, we're going to have essentially a distribution in mind. And we can also chunk this, this window of threshold voltage into several regions. And with that, we can essentially have store several bits. For example, when we want to have m bits, we need to have 2 to the power m threshold states, essentially. And then we need to also come up with several reference voltage in between to distinguish accurately which location we are looking at. So when we do that, actually, the problem is that we have limited bits of this threshold window, which make it so. Then we need to make this each of these distribution narrower, which in the end that complicates the programming step. So that's why actually when you are programming the MLC NAND flash memory or TLC or QLC, you need to spend much more time compared to SLC. That's one reason that why they are slower. Another reason is that we need to guarantee sufficient margins between adjusted VTH margin, just to make sure that we can read properly. And the problem is that after some time, these threshold changes over time after program, and they are shifted and also widened after program, because some cells actually they leak charge more, faster, some cells less. So in the end, your distribution is also getting much more, is not sharp anymore. And at some point, there might be some overlaps, like here, which in the end, when you read, you're going to see errors. But that's the case in many cases also when you read from flash memory, but hopefully ECC is able to do that. But at some point, you need to adjust your reference voltages. And that's the procedure when we do retry, read, retry. When the flash controller needs to retry the read, flash controller is going to adjust the reference voltage and then retry it, essentially. So there are works in that line also that people try to increase the performance of retryment, like retrying the reads, like how fast we can get the good or the well represent reference voltage, which can work for that state. Okay. So in the end, when we have more bits per cell, we have a higher density, but we have lower reliability and also longer latency when we work with the flash chip. Okay, so any question? I want to go through some programming, how we do programming, basic programming. So here, for simplicity, we are assuming that we are programming in SLC mode. So we have this target page that we want to program it. So other basically pages need to be, we need to apply VPass. And we also need to apply this string select line to connect that essentially these NAND string to the bit line. So these needs to be done as an initialize. Okay, and then assume that we want to write this vector like 0, 1, 0, 1, and 0. So the thing is that when you want to program, that page is actually already erased. So if you don't do anything, you have ones everywhere, right? So there are some cells that you want to write 0, which means that you want to program, but other cells that you want to write 1, you basically don't write it. So there is a procedure here in writing which we can inhibit those cells that you don't want to write it, don't want to program it. the way we can do in the NAND flash circuitry is that we connect the bit line to VCC. If you connect the bit line to VCC, you essentially inhibit that position to avoid or to escape from the programming step. Other cells that you want to program them, you need to connect the bit line to ground, essentially. So that's the thing. So we apply ground and VCC, and then we apply vProgram. If we apply the programming voltage, which is actually quite high, if we apply it at once, we're going to get to something like this. So, which is terrible. So that's why actually people, and why is it like that? Because there are some cells that they are easy to program. When you apply that 20 volt, they are basically threshold just goes high to this region. But there are also some cells that you need to wait more. Like how long you wait for that 20 volt is very unclear. So that's why people come up with this procedure, which we call it incremental step pulse programming, ISPP, which they apply programming voltage at different levels. So they apply a vProgram 0, which is not as high as the actual programming. So they first apply that and wait for some time, and then check essentially we're going to get to this essentially distribution. Some cells are programmed essentially. So after that, basically people do read. So they apply vProgram 0 and they read. And they see that, okay, some of these cells are already programmed. So they verify them as programmed. So for the next step, we inhibit those cells as well. So this one, for example, is verified as program. We inhibit it, and then we apply another program voltage, another step. And we basically do it for enough time to get to this essentially distribution. Make sense? Okay. So when we want to read from the flash cell, again, we need to, I'm going to actually have some slide later that I show more details about circuitry. Here, I'm kind of ignoring, some circuitry that we have to sense what we have stored. But essentially, when you want to read, you want to realize that if that cell is, by applying reference voltage, is on or off. That's the thing you need to do. So you apply a reference voltage, and you charge all the bit lines also to VCC. And then essentially, you need to check whether or not the current of the bit line is flow or not. So if this bit line is discharged, like here, it means that this cell has been acted as a resistor, which means applying reference voltage actually turn on this transistor or cell, which again means that this cell has not been programmed, is already erased. And then you can encode it as 1. Okay, and other cells, when the current doesn't flow, you encode them as 0, for example. So there is a sensing circuitry here that understands whether or not the flow, the current flows or not, but that part we're going to see later. Make sense? But now let's see also how we can do read operation when we have MLC. Like here in this example, we have TLC, right? We are storing 3 bits. And we want to read, for example, this CSP, which is the central bit. So not MSP and not LSP, like the center bit. We want to read it. And it's actually important that we should be able to read each of these bits actually individually, because we are storing different pages. Okay, so that's important. So here we want to, when you want to read a page, which is stored as a CSP bits of all these cells, you should be able to do that. So the procedure is that in this window, we check, we basically first come up with a reference voltage, that those reference voltage are kind of important for that CSP. So for that, we check whether or not this CSP is toggle or not. So here between this window and the neighboring window, CSP is still 1, right? So if I apply a reference 0, actually, it's not going to help me at all for that CSP. But for example, from this window P1 to P2, we are seeing some toggling. So VREF1 is important for me, for example. Again, VREF3 is also important because from 0 we go to 1, and then VREF5 because from 1 we go to 0. Okay, so these are 3 reference voltages that they are important for this encoding scheme. There might be many different encoding scheme also, but for this specific encoding scheme, when you want to read CSP, you need to apply VREF1, VREF3, and VREF5. Okay, so you start with the largest one, VREF5, and then you read. You read as if we are storing like a SLC mode, right? So you read, but you can see that when I apply VREF5, for example, yeah, this one, which is 000, is actually located here, right? So when we apply VREF5, since this state is also threshold is lower than VREF5, we mistakenly encode it as 1. So we consider that this one is 1, which is wrong, right? So that's why we need to apply all these reference voltages one by one. So we apply VREF5 and we read, and these are the output. Then we apply VREF3 and we read, and these are the output. And then we apply VREF1 and read, and these are the output. So after getting all of these, then you need to somehow combine the outputs to get the actual value that you need to do. So with this specific encoding scheme, you can see that if you XOR, basically if you do XOR of these outputs, you can get to the actual results. You can check it at homework as an option on homework as well. But essentially here you do just XORing. So XOR of this is going to be 1, XOR of this is going to be 0, 0, 0, and then 1. And with that, you read properly from this flash page. So that's why actually in MLC NAND flash memory, we actually have on-chip XOR logic internally. And so it's actually already implemented. But you can also see that bit encoding affects the read latency. So we can do some game here together. So here I'm showing 2 encoding scheme. The top one is actually the one that we had the previous slide, and the bottom one is something else. It's a bit different how you encode these states. So now let's compare the number of sensing for LSP here. So how many sensing, or when I'm saying how many sensing, it means how many reference voltage we need to apply. So for this top, we need to apply for LSP. Essentially, we need to apply 2 reference voltage, VREF0 and VREF4. But in the bottom encoding, we need to apply 4 reference voltage. For MSP, for example, in the top, we need to apply 2. But in the bottom, actually, is very good for MSP because we need to apply only 1 reference voltage. So that gives you some idea here that encoding actually would affect the latency. And again, you can think of all these data mapping based on the encoding that you have. For example, if I'm using the encoding at the bottom, then reading MSP is actually much, much faster compared to LSP. Then you can think of, okay, having some pages that they are latency critical stored as MSP, or MSP pages can be used as a cache for LSP. There are all these techniques that you can think of. And actually people are still working on that, and also coming up with some other encoding, because in the end, encoding would affect many things here also. How frequently you need to move across different, like how you move between these states, that would also affect essentially energy, and also the energy that you need to spend that go from the erase state to the P7 is much more compared to going from erase to the P1, right? Which in the end, that would also affect, depending on your data pattern, that might also affect some energy consumption for you. Okay. Question. Now, the next, I want to actually provide a little bit more detail about how we do read operations. So I will actually go over it a bit fast, but it's important to understand the sensing circuitry, because that gives some insight to you as well. So NAND flash read mechanism consists of 3 steps: pre-charging, evaluation, and discharging. Pre-charging essentially is the operation that we, as we discussed, we pre-charge the bit line to VCC. So there is a transistor here, or we can think of as a switch that pre-charge. We basically turn it on, and now the bit line is actually pre-charged to VDD or VCC, let's say here. Also, we need to apply VPass to other NAND string, other NAND flash cell. Also, the procedure of pre-charge, we also need to have this connected, like that string needs to be connected to the bit line. So all these operations that we need to do as an initialization needs to be done in the pre-charge state. So we need to do that. And after that, we essentially turn off the pre-charge key. And now, essentially, the bit line now is connected to this string. So if that string is, then we can actually evaluate. We can evaluate if this charge is actually discharging or not. Okay. So there's a sensing circuitry here that I will explain in a bit. But in this picture, actually, I'm kind of ignoring. But with that, you can understand that. And in the end, you need to also do the discharge operations. So whether or not this bit line still VCC or not, you need to discharge it anyway to make it ready for other use cases. Okay. But now let's see how we actually understand that it has been discharged or not. So with that, I'm using this picture here. It might be a bit complicated, but bear with me. I think you're gonna figure it out. So before the evaluation step, which means in the pre-charge state, the chip initializes the latching circuitry. So here we have this bit line, and here also is connected the NAND string, which I'm not showing here. So there is also NAND string here connected to bit line. And we have, so this is the latching circuitry. There are two transistors here, M1 and M2. And I should also say that this is one example of doing that. We don't know exactly, for example, how they implemented in NAND, real NAND chips, but there are some patents that based on those patents, we can, get some information about it. So let's look at this latching circuit. So there is this back-to-back NOT, and we have also two transistors here, and this also is connected to ground using another transistor. Okay, so now we have some sense of it. So when you pre-charge it, you essentially also need to activate transistor M1. So this transistor is going to be on. So when you turn this transistor on, this bit line is actually already also VCC, right? Because we charge it. So bit line is going to be VCC. So this capacitor here, you can think of as a parasitic capacitor, or there might be also a capacitor really there. This capacitor is going to also have the voltage high. So since this voltage here is high, this is going to also be turn on this transistor here. Okay. So connection to the ground is established. So now we have connection to the ground to V out bar, because M1 is also activated. So that's why V out bar is going to be 0. And then V out is going to be 1 because it's going to be kind of not back-to-back not. So we know about it, right? Okay, good. In the evaluation step, what we do, we essentially, we need to disable pre-charge transistor. And then also we disable M1. But this time we actually enable M2. Okay, so M1 is disabled, but M2 is activated now. So now depending on the state of this SO, so if the charge here decharge in the bit line, then actually SO will go from 1 to 0, right? So when it goes from 1 to 0, this transistor is going to be turned off. So when this transistor is off, the connection to the ground is not established. So it doesn't matter that I activate M2. V out is going to keep its charge already. So it was 1, and I still get 1. So that's why when we actually drain charge through the bit line, which means that that cell has been erased, we actually encode it as 1. And if that charge didn't drain, it's going to be still 1. And this transistor is on, and the connection to the ground is still established. So that's why V out will go from 1 to 0. And V outward is going to be also 0 to 1. So that's latching circuitry that we can learn, and we can actually understand whether or not we stored 1 or 0. Does that make sense? Okay, very good. Interestingly, actually, we can also implement inverse reading, which interestingly, we can actually do NOT operation using this. If you just switch the basically the activation of these M1 and M2 transistor in a different, other way around, you essentially first activate transistor M2 and then disable it and activate transistor M1. There you're gonna read the reverse value. And with that, you are actually implementing NOT with the NAND flash chips. Okay. Question. Okay, now we can actually get to some performance numbers. I think now we have a good understanding of how flash cell works, how we can write, how we can read. But now let's see, learn more about the latency. What are the parameters that affect the performance of the SSD essentially? So latency or response time, the time delay until the request is returned, we have average read latency, which is reported actually in some sources, like around 67 microsecond, and average write latency is actually 47 microsecond. So you can see that write latency is actually is lower even compared to read, because you most of the time you write only in the buffer, the write buffer. And also people report throughput as another metric, and that throughput is actually reported with the number of requests that can be serviced per unit of time. So they usually call IOPS. If you might also already hear about IOPS, is the number of IO operation per second. So input output operations per second is actually very much used when you want to report the performance for random read and write. So for random read throughput, SSD can, for example, provide up to 500,000 IOPS. I mean, again, for this specific SSD, Samsung SSD 980. And random write throughput is up to 480K, for example, IOPS. We also have another metric, which is bandwidth, which is the amount of data that can be accessed per unit time. So here we actually care about exact amount of data, like how many bytes. And that's actually used for the reporting the bandwidth for the sequential read and write. So when you have sequential read, meaning that you want to read several pages, that you have a large request, then you can actually use this metric also to get the, to judge about the bandwidth of the SSD. So they usually report with megabyte per second, gigabyte per second, for example. Okay, makes sense? So, and all these numbers are actually much better compared to hard disk drive. Like the latency for HDD is around 5 to 8 milliseconds. Throughput is something around 1,000 IOPS, and the bandwidth is something around 100 megabyte per second. So that's why SSD is very much in the field now, right? They are much better than HDDs in terms of different metrics of performance. Okay. Yes. Well, I mean, not necessarily, because when you read, I mean, throughput is different from latency, because with throughput you're making it. I mean, there's a pipeline, and then you're not paying for that latency much. There are other things that can happen actually. I don't exactly know why it's like 480 and that's 500, but yeah, you cannot really exactly judge based on the latency. So bandwidth and throughput are very much, I mean, in the same line here, right? Yes, of course. Yeah, so yeah, I don't remember actually. I don't have these numbers on top of my head. I don't remember exactly why, for example, read bandwidth is better or worse here. But essentially, the latency is a bit is independent. I mean, not fully, but a bit not that really related to the throughput and bandwidth. Okay, so NAND flash chip performance also, when you want to understand the latency which happens for each operations, we have different parameters. One is TR, which is latency of sensing from the cells when you want to read, like that latency that you apply reference voltage, and then you sense and fill up the page buffer in the NAND flash chip. You also have another latency, which is programming latency, the latency that you need to take to program your cells, and also latency that we need to when we want to erase a cell. So TBER is also another one. So these numbers actually varies depending on the MLC technology, like how many levels you are storing in each cell, processing node, microarchitecture, how they design that NAND flash circuitry. So in 3D TLC NAND flash, for that Samsung, for example, SSD that I discussed about it, we have, I mean, roughly these numbers, like TR is around 100 microsecond, programming latency is 700 microsecond, and erasing latency is 3 millisecond, for example, just to give you some idea about it. Another important performance metric for flash chip is IO rate, number of bits transferred via a single IO pin per unit time. So flash chips actually has only 8 pins, 8 IO pins, I mean, at least nowadays. So a typical flash chip transfer data in a byte granularity, because you have 8 pins, so you transfer byte by byte. So when we have a 1 gigabit IO rate and 16 kilobyte page size, then the transfer latency, which is DMA, the latency of moving data from NAND flash page buffer to the controller, is something around 16 microseconds. Okay, so you can just do some calculation here easily. Yeah. So now let's see some example. When we want to do, for example, a read operation, there are some operations that we need to do. We need to send the command, the read command, to the NAND flash chip. So that latency is actually very low. So that's why we can ignore it overall. Then NAND flash chip needs to do the TR, which is the sensing operations. And after reading that, we need to data needs to be moved to the controller. So we have this TDMA latency. In the controller, we need to do ECC decoding, and also we need to do this de-randomization, okay, for read operations. So these two, command latency and randomization, if we can actually ignore them because they are not very large, in the end, it's going to be at least 136 microsecond, for example, latency for reading. And when you are programming, you need to do randomization, do ECC encoding, and then send the write command, and then send your data in a DMA latency to the NAND flash chip, and then you do the programming. So if you just sum them, you're going to get to the latency of 736 microseconds, for example, for this example. And you can also calculate bandwidth, for example, like when you do read 16 kilobyte of 136 microsecond, you can get the bandwidth of 120 megabyte per second, or similarly for write. But now you can actually, you're observing actually very much difference between the numbers that we discussed in the previous slides and the numbers that we are calculating. And the thing is that that latency which is reported there is actually kind of an average latency, which can be also, you can consider effective latency, because you have parallelism. You are not writing to one flash chip. On average, you can get much better latency. And when you want to also calculate the bandwidth, again, you have a lot of requests. So there are a lot of optimization going on with advanced commands that I'm going to also discuss it in a bit. But we have internal parallelism, and we also have advanced commands that we can optimize these latencies to get better performance. Also, we might, for write, for example, specifically, we don't necessarily write in the flash chip. We usually use the write buffer. And that write buffer does not need to be also always DRAM. In TLC NAND flash memories, since TLC is actually very slow, part of that you can also consider as SLC programming. And that SLC part, you can use it as a cache. And this is actually implemented in the vendors, in the commodity SSDs. Okay, so there are some advanced commands that they are important to improve performance. Let me see. Okay, so one command is actually for a small reads. So minimum I/O units in modern file system is 4 kilobytes. But there is actually latency and bandwidth waste due to I/O unit mismatch. So the thing is that in modern SSDs, for capacity reason actually, and also for cost reason, to make it low cost, usually the page size is actually 16 kilobytes. But but in the operating system, file system is actually 4 kilobytes. So now you have some mismatch here. So when you read a page, you're kind of unnecessarily you're reading 12 kilobytes of data. Okay, so that's one of the things that you can avoid. So for that, actually, there are some optimizations. Like one is the sub-page sensing. Is actually patent for Micron, and I think it has been adopted. So in Micron, you can have this, they call it a snap read operation. So they changed the microarchitecture, did some optimization, which you can essentially read only that subpage that you want. And that would affect reducing the sensing time. You don't need to spend long sensing time for reading 16 kilobytes. You can only spend enough time to read, for example, 4 kilobytes. So I'm not going into detail of that, but just to give you some idea that there are optimizations that people can use in order to reduce the latency for sensing. Another optimization is random data out. So you assume that you read the 16 kilobyte and you have in the page buffer, then you don't need to send all the 16 kilobyte out of the memory. You can just send arbitrary offset and size from that page buffer, which that reduces the latency of transferring and also the ECC decoding, essentially. Okay. Another interesting optimization is actually cache read command. So normally we have these kind of operations when we want to read a page A. So we have TR, TDMA, and TECC. And then when we want to send another read command for another page B, we can actually start sending it as of here. When we are done with TDMA of the previous read, now the channel is actually available. So we can actually send, we can start sending the read command to the NAND flash chip and do this TR and so on and so forth. So essentially, only the ECC is actually kind of overlapped here between these two reads. But there's another optimization that people is using, which is cache read. When we are sending the command for read A, we are also sending the cache read command B to the NAND flash chip, saying that you need to give me the page A, but after that I also need the page B. So we are kind of overlapping these operations, and with that we can actually overlap TDMA and TECC. So here in this picture, I'm showing a little bit more detail. So we are sending page read A, and then we do this page sensing. So we have page A in the page buffer, and at the same time we already send the cache read command for B. So when we are done with the sensing of page A, we can actually start sensing for the page B. And we have enough write buffer. So we have another page buffer that we can, sorry, not write buffer. We have another page buffer that we can do the sensing of page B into another page buffer. So with this, you can actually overlap some time. And it doesn't come also free because so we are adding page buffers. So some of these optimization techniques, they need actually more buffers to be added inside the flash chip. So with cache read command, we can remove TDMA from the critical path and increases throughput and bandwidths. This also reduces effective latency. So latency of one operation has not been changed, but effective latency, like assuming several requests you are sending, so the overall latency that you are getting is actually lower, which is good. But at the same time, it's not also free because you need to add page buffers. Make sense? Another operation which is multiplane, which we also discussed it in the past. I mean, in the previous some slides ago. Essentially, planes share word lines and row column decoders. So when you have this target page in plane 0, if you're actually also you're targeting other essentially pages in other planes as well, you can actually send multiplane operations. So you can do the sensing of several pages in parallel across different planes. So that's the opportunity, and we can get, but the constraint is that only for the same operations on the same page offset, we can do that. So the controller needs to understand that, okay, you need to, now we need to address several page, like several reads, and these reads are going to the same die, different planes, and all of them can be addressed by multiplane operations. And then the controller, when send the request to the NAND flash chip, is sending multiplane operations. It can be for read and write also. Doesn't need to be only for read. Okay, question? I mean, to some certain, yes. I mean, a bit different, but yes. But in subarray level parallelism, you don't have this constraint that you need to access the same row in different subarray, right? But here, for example, you have that constraint. Okay, so multi-plane operations, of course, has benefit, increase the throughput bandwidth almost linearly with the number of planes. And yeah, here, for example, when you do this operation for 2 planes, assuming. So first, we need to, when we want to do write operations, for example, here is the example, right? Yes, we want to program a multiplane, and we have 2 planes. And the page that you want to write is 16 kilobytes. So now you need to transfer 32 kilobytes of data. So that's why we are writing 32 kilobytes. The latency we need to spend is the program latency is actually in parallel completely. So 700 microseconds for both planes, which is completely in parallel. But then you also need to do this TDMA for both of these pages, right? Because you need to transfer 2 pages. So now you have 16, you need to add 116 here and also another 16, which is already added here. And for ECC encoding also, you need to do for both. So you have 20 and also one added 20 here. So that's the latency, the total latency that you're getting. However, since program latency is actually very much the bottleneck here, it will give you very good performance in the end. So you can see that by multiplane write operation, you are increasing the throughput by 2, for example, if you have 2 planes. So it is also very interesting to think about it, that per operation latency actually here is increases. Because when you want to write 1 page, you're also sending another page, so you need to wait more to do it completely in parallel, right? So that's why the per operation latency actually here is increasing, but with the overall performance latency is reduced. So that's something that you can also think about it when you want to optimize. Sometimes we care about each single latency, but sometimes we care about the overall latency. Yes. It could. And that's why actually the procedure of garbage collection, we're going to get to that later, needs to be aware of multiplane operations. Yeah. Very good question. Any other question? Okay. Another important optimization is actually program and array suspensions. So read performance is actually often more important because reads are usually on the critical path of the processor. So, and writes can be done in an asynchronous manner using buffers. So we write to the buffer and then we just inform the SSD that we are done. Sorry, we inform the host that we are done with the write, and we can do that write operation asynchronously in the background. However, a read request can be returned only when the requested data is ready after reading the data from the chip. So the problem is that we have significant latency asymmetry here. Read latency is 100 microseconds, but program latency is 700. And raising latency is actually, I said 3 milliseconds, but it's actually usually around 5 milliseconds for that specific SSD. So now you can see that also if the chip is designed to program all the pages in the same word line at once, meaning that, so this SSD is TLC, right? Is a TLC NAND flash. If you want to program all 3 pages at the same, which is usually is like that, you need to actually spend 2100 microsecond to program all these pages. So the worst case chip level read latency can be 50 times longer than the best case latency. So assuming that you are very unlucky and that read is actually is queued after a write operations. So that's very bad. So that's why people try to suspend an ongoing program, which can be also ongoing arrays, once a read arrives. So here in the example, we have a program going on, and then we need to do read. So for the program, we are spending 700 microsecond, and for read, we need to do 100. So read arrival is actually at this position. So now the latency that the read is actually experiencing is also 700 microseconds. However, if we can suspend, so we do program, and then we suspend it, we service a read operation, and then we retry, we continue the program from the part that we actually suspended. So then the program latency is going to be 800, something around that, but the read is going to be 100. So overall, you can see that we are getting much better performance here. So it has pros, like significantly decreases the read latency, but it comes at the price of additional page buffer for data to program. So now when you want to suspend, there should be some, additional buffers, such that you can do that suspension. And also this complicated IO scheduling until when we can suspend ongoing program arrays. This actually comes at the price of fairness issue, which we're gonna get to that actually later. And it also has negative impact on endurance. So this suspension and resuming actually would basically has negative impact on endurance of the NAND flash set. So it's not free, and it comes with some overheads, but suspension is very interesting technique that people are using now. And this is a summary of these techniques that I discussed. Question? Okay, so I think it's a good time actually to get another break. Let's be back at 3:10. This time we have 12-minute break. And then we will continue with address mapping and garbage collection. Hey, can hear me still, right? Okay, great. So let's get to address mapping and garbage collection. We discussed about flash translation layer overall, but it's another like kind of a recall for you. So SSD firmware refer to a SSD controller and provides backward compatibility with the traditional hard disk drives by hiding unique characteristics of NAND flash memory. So there are a lot of characteristics that NAND flash memory has, and FTL actually makes it easy for the operating system to work with SSD by hiding all these complex things. And it's actually responsible for many important SSD management tasks like address translation, garbage collection, word leveling, data refresh, and I/O scheduling. And we kind of discuss about different things here, the high level, but now we'd like to see about address translation and garbage collection. So here you can see a simple SSD architecture, and the host actually, the way that looks at the system is actually a storage view at the operating system is a flat block device. Here, for example, you have 16 blocks, from the operating system. And this actually flat block is, you can chunk it or categorize it to logical block address. So LBA is logical block address. At the hardware in the SSD, we have different flash chips, different blocks. And in each block, we can call it physical block address. So we have 5 blocks here. I mean, this is an example, 1 flash chip, 1 plane. And in each block here, for example, we have 4 pages. So physical page address, we have page 0 until page 19. So by checking these, actually, you can see that we have over provisioning. Physical capacity is larger than logical capacity, which actually kind of the case for when you use SSD. So you have actually more capacity, but you cannot use that. So when you buy a 1 terabyte SSD, that internally might be actually much more than 1 terabyte. But that needs to be used for performance and lifetime. For performance, for example, as I said, for out-of-place writes, out-of-place updates, you should have over provisioning to just write somewhere else. And if you don't have that much space, reserve a space for that, then you need to invoke garbage collection more and more often, which will come as a performance overhead. And also, when you have much more reserve space, you can potentially use that also for lifetime reasons. So when some blocks are dead, there are some other blocks that you can use them. So that's why actually SSDs actually have very much actually over provisioning. I don't know exactly actually how many blocks they have, but you can think of actually a lot. So now let's see how we handle page writes, for example. So the host sends a write request. So the logical block address is 0 because we want to write to this location. And the size is also 1, so we want to write only 1 sector. And the direction is also right. And the data that we want to write is A. So that's a request we send to the SSD. And essentially, SSD writes that in the block 0, page 0, assuming that all pages, they are all free. So we write there. So now we are assuming that logical block size equals to physical page size. Like physical page size is 4 kilobyte here for simplicity. But later on, we're going to see that actually logical block size is 4 kilobyte and physical page size is 16 kilobyte. So there has to be something there to done. But here, for simplicity for now, assume that these two are not, they are fixed. They are equal. So later on, you get a bigger write, sequential write, or sequential large write that you want to write from start of logical block address 4, and the size is 12, like 12 sectors, or 12 logical block address that you want to write, and also the data, the burst from B to M. So when you look at the SSD, you might think that, okay, this logical block address 4, so I also have this physical page address 4, so maybe I would just write from block 1 to block 3, right? But in reality, actually, that doesn't happen. And the SSD actually keeps writing from the same block that we had open. And that's the reason that basically we want to keep the number of active blocks less. So when you have an active block, meaning that the block is active to be written, then actually you want to have only one block being written at the same time, and due to the open block problem. So you might have several flash chips and flash dies, and they have several blocks open to write. But for one flash plane, you want to have only one block being written at the same time. There is a problem which is called open block problem. If you want to learn exactly about it, you need to check, the papers or studies on the line of reliability of flash chips. But actually, people report a lot that if you have several blocks open and you can write to them, actually, that would come at the reliability issues. Another constraint is also program sequence. So here we don't see it much, but essentially we try to write actually in a fixed program order within a block. So for example, we don't write to, let's say, page 2, and then we write to page 1. We try to actually have an order in writing. That's also because of cell-to-cell interference, which you're gonna actually learn about it more in the next lecture. So now the problem is that the logical block address does not match the physical page address. And so when we receive a read later on from logical block address 4, then we want to send the read, but we don't know from where. So that's why we have this mapping table, logical page address to physical page address. So by querying this mapping table, we know that it's going to be physical page address 1. So essentially, we send a read to that, and we get the data. So sometime later, we receive another write, which is actually kind of update, because you're rewriting to the same logical block address with the different data, or prime. So with that, what FTL does is actually it writes this update to the next immediate free page, which is available here, which is here, page 13. So we just write to that, and we invalid actually the previous block, the previous page that we had. And as we receive more updates for that, we actually keep invalidating and writing to new pages, like free pages. And at some point, we are running out of free pages. Okay. And we don't wait to be completely run out of free pages, and then we start them. So there should be a threshold that we essentially invoke the procedure garbage collection to reclaim free pages. So the things that erase unit is a block. If a victim, so we need to, essentially garbage collection need to make sure that we can erase the whole block, right? That's the procedure. So if a victim block that we want to erase it has valid pages, all valid pages need to be copied to other free pages. And then there is a performance overhead here. Actually, it's the most important performance overhead of garbage collection, which you need to copy available valid pages from one block to another block. And that also comes at a lifetime overhead, because now you have additional writes, which is because of, and that will increase program erase cycle increase. There is interesting thing about SSD, which we have write amplification. With HDDs, the number of writes that OS sends and the number of writes happen in HDD is actually equal, right? But in SSDs, we have OS sends some writes because of the application, but then internally we have more writes compared to that writes. So that's called write amplification. And people try to keep it as to 1 actually as much as possible, like have equal number, but in the end it's not possible, because for garbage collection you are copying data, and that will cause some internal writes, essentially. So there might be many different actually policy for garbage collection. One policy that you can think of is greedy victim selection policy, that we erase the block with the largest number of invalid pages. So the key insight here that we want to minimize the overhead of copying data. So we go with the block that has the minimum number of valid pages, okay, to copy less. So in order to implement that, we have a status table that for each block address, a physical block address, we need to keep the status, whether or not, what are the pages that they are free, what are the pages that they are invalid, and what are the pages that they are valid, okay? So for block 0, for example, we know that page 0 is invalid, and the other pages are valid, because they have the valid copy of data. And for block 4, for example, we have 1 valid, and then 3 is free, okay, because we haven't written to them yet. So by having this status table, FTL can see that block 3 has the lowest number of, or highest number of invalid pages. So essentially, block 3 is going to be considered as a victim block. So we need to copy essentially the only valid page that we have in block 3 to the free page, which is 12. So we read this data from physical page address 12, and then we program to free page that we have in block 4. And then we also need to update the status in here. So here the block 3 status is all invalid, and the status of block 4 is going to be valid, and then through 2 free pages. And also we need to update the mapping. So because now we write M to another location, so we need to also update the mapping table. That logical page address 15 now is mapped to physical page address 17. So now actually here we have a problem, that how FTN knows physical page address 12 is actually mapped to logical page address 15. Because we keep this table from the other way around. When we have the logical page address, we can query this table and get the physical page address. But here you have the physical page address 12. So now you want to understand what's the logical page address for that, such that you can update the correct entry in that table. So one way would be to keep another mapping, which is physical to logical also mapping, and you keep it consistent. But actually, the way that people do is using out-of-the-bound area. So in each flash page, we have some out-of-bound area, which has been used for some metadata. That part actually can be used to store the logical address, which is mapped to that physical location. So by reading, essentially, when we read from physical page address 12, we can get also the logical page address from that because it's already stored. Okay, makes sense? And so after that, we can actually essentially erase block 3 and make block 3 all free, which can be used for future writes. Here also we have the procedure, which we call it lazy erase. When you erase a block, you actually make that block ready to be write. So that's the open block problem again. So we don't immediately erase block 3. We just do it when we really need to do it. So when a garbage collection actually kicks in, try to make some block which is ready to be erased, but we don't erase it immediately. We just wait until we really need to do in order to make the number of open block at this to some certain point. Make sense? Okay. So now let's get to some performance issues of garbage collection. So garbage collection significantly affects SSD performance because of high latency, large block size of that we have. So like even if in some SSD, for example, a block contains 576 pages. Even if we have only 5% of the pages in the victim block valid, it's going to be actually around 28 pages. So there are 28 pages that they are valid and we need to copy them. So the latency of that copy is actually going to be 27,000 microseconds, something around that. So that the latency is actually huge. So which is actually orders of magnitude larger than latency of reading and programming, and even actually is also larger than erasing. So that's why with garbage collection, the main contributor of the GC latency is not actually the erasing operation. Erasing can be done actually in the background, sometime, but that copy is actually on the critical path. So if FTL performs GC in an atomic manner, meaning that if FTL start GC, basically FTL does not service any requests anymore until we are done with the GC, then actually it can delay user requests for a significantly long time, long tail latency, performance fluctuation, and also noisy neighbor. You can think of having there are two applications running together. One application is write intensive, the other one is read intensive, let's say. because of that write intensive application, that application causes a lot of GC operations to happen. And those garbage collection is also affecting the performance of that read intensive applications. Okay, so this kind of a noisy neighbor. So there are some mitigations going on here. One is actually using some command, which is actually specified at the OS level, trim command, which was not before actually in the HDDs. So when people start to use SSD more and more, some people also try to also improve the OS kernel, like Linux kernel, to basically to be more aware of SSD. So one thing here is that, for example, in HDD, when you at the OS, when you just delete a file, that is going to be only deleted from the page mapping address, essentially. But that file is still located in the SSD, meaning that when you have garbage collection, SSD will consider that file still as a valid location and will keep copying it to another location. By using trim command, actually, you can inform the SSD of deletion or deallocation of a logical block, and that allows FDA to skip copying of obsolete data. That's very interesting, which is already also implemented. Another thing is that people try to do garbage collection at the background. So they try to understand when the SSD is idle to invoke garbage collection during idle time of SSD. This might be actually possible for general purpose computing, because each person has some working hours and we can know when it's idle. But it's very hard to do in a cloud system, and a lot of people are accessing the same storage. So there are a lot of works going on to predict the idleness using heuristic machine learning techniques that people try to predict when the SSD is idle to essentially schedule garbage collection. Another way is to using progressive GC, which means that we don't do garbage collection in atomic way. You can think of suspension. We do, for example, when we want to do copying of 28 pages, following our example, we copy one page and then we service one request. Then we copy another page and then we service another request. So if you do that kind of progressive garbage collection, then it will basically, it wouldn't affect significant latency for that application. Okay, so that's called progressive GC, to divide GC operation into subtasks. And this has been also implemented. And that's why actually in the past, when we were profiling the performance of SSD, we had, for example, very good performance. And at some point, it was super clear that now garbage collection kicks in. And now the performance was just so low. But now it's not that actually dramatic. So you can see that the performance is okay. And then now we have GC, okay, we have a lower performance, but it's not that dramatic that, for example, the user may not actually feel it anymore. Question? But the thing is that garbage collection needs a lot of copying data. And that copying actually also puts a lot of pressure on the internal bandwidth of the SSD. Like you need to use all these channels to move data from one to another. There are that thing actually is kind of also implemented through you are thinking about like cache read command, right? You can actually fuse one GC operations with one read. This is very similar to progressive GC. So when you are want to do one GC, one copy with another also read operation, for example, you can also be more intelligent and use also other optimization techniques. You can even do multiplane operations, for example, right? So there are optimizations going on there as well. Okay, yes. 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 No, because here we are not suspending. If you think about it, we are just saying that, okay, I need to copy 28 pages. I'm not going to copy 28 pages in an atomic way, which I'm not like servicing any other request until I'm done with that copy. Yeah, but that copy is just read operation. I mean, you can also think about writing, but that writing is not you're not suspending that write operation, right? Your copy is reading and writing, right? but you are not suspending that write operation. You can do that also potentially. That actually is happening. Yeah. Very good. Okay, so remember that we discussed about this mapping, which I said that for simplicity, we consider that page size is 4 kilobytes, such that everything is simple. But in reality, in most of the SSDs, let's say capacity optimized SSDs or cost optimized SSDs, they are actually using page sizes of 16 kilobytes. But our requests are 4 kilobytes. Now we have the problem of I/O mismatch between OS and NAND flash, which the page size is 16 kilobytes, but the logic block is 4 kilobytes. So how we are handling a small write requests? So there is here inefficiency due to erase before write property. I will walk through it using an example actually again here. So you have here, consider that you have in your one plane, you have these 2 blocks, for example, and physical page address 0 to 6, and you have 16 kilobytes of page size. So you receive a request that you want to write for only one sector, meaning that only one 4 kilobyte data. And here is also your mapping table, which you are storing mapping information per page. But that page is 16 kilobytes here in this example. So the address which we receive here for logical block address is stated here. So if you encode it here in binary, you can see that. And then you can see that, okay, the offset is 0. And the page number is actually 1. Because we can store 4 OS pages at each physical page. That's why we are using 2 bits as the offset here. These 2 bits as the offset for that specific page. So in the mapping table, we go to the logical page address 1 because it's actually page address 1, and then we wrote here A, and then we put also 0, 0 here, like the physical page address 0. So this mapped to that. Makes sense, right? Later on, we receive another request to write. So now we want to write 2 pages, B and C, to logical block address 1. So if you encode it in a binary, you're going to see that it's going to be page number 0 with a page offset of 0, 1. So in the mapping table, you're going to come up with another logical page address. So now the thing is that here you can think of writing B and C actually after this, right? Because they have a different offset. I can actually write it. But this is not happening in SSDs. And the main reason is actually that writing B and C after A is going to be, so there are 2 things here actually. First, so we write B and C in this location. So not starting from exactly this location, because we want to keep the offset aligned. That's easier to handle. But another question here is that why not using the unused space in a physical page here? We have unused space. Why not writing B and C here? So the thing is that data space is already mapped to logical pages 5 to 7 because of here, right? So we mapped the logical page address 1 to physical page address 0, and that 1 can be 4, 5, 6, and 7. Okay, so already 5 and 7 is already mapped here, so we cannot remap. We cannot map B and C to that. Okay. So later on, we get another write operation to the same what we have before, logical page address 1. But now we want to write data D in the offset 3. So can we write here? Potentially yes, right? We can write, but in fact, we cannot. Because first, because of data randomization, cells in the unused space have been already programmed, probably. That's the program procedure. And another thing is that actually program order constraint is actually more important here. So we already write A, and then we write B and C at this another page. So now if you want to write again at the page 0, that's actually violating the programming order, which would cause actual reliability issues for B and C. So because of that, actually we don't do that, and we essentially discard. We need to read A to the DRAM, and then we modify it with the data D, and then we write the whole block, the whole page again on a separate page address. So that's the procedure we need to do if we don't use fine-grained mapping. I mean, so far I'm saying that we are using this mapping, which is not fine-grained. You're gonna do that like that. So that a small write called read modify write. This is actually called read modify because you read, you modify, and then write, which wastes of P cycles plus additional read operation, and in the end, performance and lifetime degradation. Okay. So the way people handle it is using fine-grained mapping plus using also page buffer. So first of all, we keep the mapping actually per small page, per 4 kilobytes. All these actually pages here, they have address. So that's one thing. Another thing is that we try to keep data, accumulate data in the page buffer. So we essentially wait for some time to have enough number of pages in the page buffer, such that we have 16 kilobytes of data, and then we write it, flush it to the NAND flash page. Okay, so with that you can essentially avoid that issue. And this actually can be even mapped to super block. So here you are considering one block, you are managing one block, but there might be several blocks together, and you actually map it. You try to write it all at the same time together. But we're gonna get to that maybe later. Okay, so this will comes at the price of larger mapping table. So in the past we had 16 kilobyte of mapping, 4 bytes per 16 kilobyte page. So the overhead was much less. But in 4 kilobyte mapping, the overhead is 0.1% of the total SSD size. So that would complicate, and we need a larger DRAM capacity. But in the end, that's very important. And that's why people, despite non-negligible drawbacks, fine-grained mapping is widely used in modern SSDs due to its high benefits. Question? Okay. Then I will continue with multiplane operation aware block management. So recall about multiplane operation, and also recall about what your colleagues asked about, that garbage collection can mess up the multiplane operations. So you can actually do the block management and garbage collection aware of multiplanes. So essentially, when we want to write, we have one. So when we receive a write, for example, we have for one plane, we can wait for more writes, and then flush it to the multiplane or using multiplane operations. So with that, you can actually use, benefit from multiplane operations when you're writing. And that's the concept of super block-based block management. So it does not need to be only one block. You can actually, have several blocks together and then try to manage it together. But now how we can manage it with our greedy policy here for the garbage collection. So here is our full block, and these are the number of invalid pages. So the victim block is going to be this one, and then we're going to copy them, and then essentially we need to erase it, right? But in the multiplane operation, so here I'm showing the different blocks in plane 0 and 1, and you can see that the free pages and invalid pages. So here we can essentially, if we go with the victim, with a greedy policy, we're going to see that, okay, in this plane, block 2 is actually a victim because it has the highest number of invalid pages. And in plane 1, we have block 1 as the victim. So now we need to do some copy, and then we need to do, several copy. So I'm not going into detail of these operations. Most of them, they're going to be single plane read because they are not aligned, right? So you need to do several single plane read from this and that. and then some you're writing them to the other plane, to block n-1. Also, in order to, if you consider block n-1 is going to be the future, I mean, for some time is going to be your writing location, right? If you want to benefit from multiplane operations, you should actually discard the first two locations, like available locations of block n-1 in plane 1, such that you can continue writing multiplane. So that would come as a capacity overhead, essentially. However, we can do it more intelligently. We can benefit from super block-based management. And we can say that, okay, these are two blocks in two planes. I'm going to count the number of, essentially, the number of invalid pages together. So now you select a super block which has the highest number of invalid pages. So here we're going to select this one, because it has 7 plus 2 is going to be 9. So it's going to be the most, the victim block, the victim super block. And then now you can see that actually you can do some single plane operations, and also you can do some essentially multi-plane operations as well. For example, this location, right? So that would, basically give you some performance or improvement when you do copy using multiplane operations. And when you want to write to the positions, when you read, and then when you want to write, you can actually do a lot multiplane write operations, which will be give you better bandwidth in the end. And you can actually also extend this idea across several dies. It does not need to be only one die and multiplane. So this super block can actually expand through several dies that can be operated. So multiplane operations can significantly improve SSD performance, but requires proper management in FCL. So FCL should be aware of that when doing garbage collection and do block management, such that we can benefit from multiplane operations. Make sense? Very good. Okay, I'm happy. So I was telling Maria that I need 15 minutes to go over IO scheduling and flash memory parallelism, and I have 20 minutes now. I mean, less, 18 minutes, which is good. So IO scheduling, actually, we already discussed it. We already discussed Flynn paper, if you remember. So I'm not going actually into a lot of details of that. I'm going to only pause in the on the basic, essentially, the parts that we discussed about sources of unfairness. Remember that we were discussing about, okay, now in SSD, in the past we had SATA, and the OS was handling this IO scheduling for us. But with NVMe, which is very important for SSDs, we actually push the queues to the SSD device. And now there is no actually kind of a scheduling which can potentially ensure fairness and high performance for SSD device. And we actually show that we have unfairness. So for that, we actually use real studies. And we run 2 applications on modern SSDs. And we observe that, essentially one application can slow down much more compared to another one, which is a fairness issue. I'm going actually relatively quickly because we discussed all before in the memory controller lecture. We actually discussed about different sources of interference. So here I want to actually slow down a bit because back then we couldn't discuss in detail about these sources, but now we can actually discuss a bit more. So IO intensity is actually one of them. Like when we have different flows with different IO intensity, they can potentially affect each other. So we discussed that one flow, for example, is fixed, and another flow is actually, we can increase the intensity or by increasing the number of megabyte per second that you want to write. So at some point it will cause the increasing the queue waiting time, and the other queue will experience a lot of latency. So the queue wait time highly increases the IO intensity, and that would cause unfairness. And we actually also show how unfairness is happening when you increase the intensity of the interfering flow. Another source was different access patterns that we discussed about some applications, they can benefit from even distribution of transaction. But some of them, they don't. So it's such things happen. Actually, the application Blue is going to actually slow down much more because in the past, Blue can be serviced fast because of the parallelism, but now it cannot because it needs to wait for Red application. And that's also another source which causes unfairness in real scenarios. We also discuss about read and write ratio. So when we have two applications, that one of them, you can tune how the intensity of the write operations. Like the interfering application can have 0% write to 100% write. And here you can actually see the fairness of this the interfering application. And essentially, when flows have different read-write ratios, existing schedulers do not effectively provide fairness. Garbage collection, we already discussed about it, which some flows actually cause a lot of GC. So we can call them high GC flow. Flows with a higher write intensity induce more garbage collection activities. And that can potentially cause performance degradation for the neighboring inference. So we discuss about these fairness issues. And then we come up with the Flynn technique that we discuss about the technique, such that we can reorder these flows in the fairness aware queue. So you can reinsert them. So here we want to, when we receive, so from high intensity flows to low intensity. So blue is requests from low intensity flows, and reds are high intensity flows. And when you receive a request from low intensity flows, you actually insert it in the head of the queue, such that you can address it faster. And for the second stage of the Flynn controller, we discussed about, there should be a mechanism to enforce priority levels that are assigned to each flow by the host. So the host system might want to prioritize some applications. So Flynn needs to also ensure that. So that's the stage 2. And in the stage 3, we try to make sure that we have weight balancing and transaction selection. To essentially, it's always good for performance. Most of the time, it's good to prioritize reads over writes. But at some point, that write is also quite poor because that write has been waiting for a long time. So at some point, we realize that, okay, maybe now it's worth it to prioritize writes. So that's a kind of a read-write ratio, and also for garbage collection, how we handle it. Okay, and then, we compare against prior work, and we show better performance and better fairness compared to prior works. And that's a very quick overview of I/O scheduling. Question? Great. Okay. Another one is actually flash memory array parallelism. I really love to discuss about it as well because it's very close to my heart. This work that I call it with Rakesh, we call it Venice. And you're going to see why. So the motivation is actually that in SSD, we have SSD controller. And there are flash controllers that are connected to flash chips by some channels, right? So now these channels are shared. So now we have the problem of past conflicts in modern SSDs. This one is actually similar to subarray level parallelism, that we have some shared circuitry that they cause some conflicts. So multiple flash memory chips are connected to the SSD controller using a shared channel, and I/O requests attempt to simultaneously access the flash chips using a single pass, which is going to cause pass conflicts. And pass conflicts cause I/O requests to be transferred serially on the shared channel, essentially. And that essentially limits SSD parallelism and reduces performance. So here we try to actually show it with this example that, for example, flash controller 0 wants to handle read request 1 and read request 2. And they are actually needs to go to different flash chips, but now they need to wait for each other. However, if we have, we can map that to different channels. Like read request 1 can be handled by flash controller 0 and read request 2 can be handled by flash controller 1. I mean, ideally, if they can go to different channels, then we can actually handle them completely in parallel and we save cycles. Okay, so we wanted to avoid that. We actually did some analysis and see that pass conflicts increase the average I/O latency by 57% in our experiments, and the performance overhead of pass conflicts increases by 1.6 times in our experiment for high I/O intensity workloads. So there are some approaches. So basically, our key insight here was that we don't have enough connectivity inside the SSD. So we need more, let's say, path diversity inside the SSD such that you can try to route your different requests to flash chips. So that's why we try actually look into some prior approaches that can be potentially used in this for this idea. So we look at the baseline SSD, which I mean, this is kind of a shared channel, so there is nothing different here. There are some works that they do packetized SSD. What they propose is actually very interesting. They essentially say that we have some control pins and also we have I/O pins for each flash chip. Potentially, you cannot use control pins for sending data, right? But they say that we can actually implement some functionality of control in the flash chip. So they add controller per flash chip, which actually comes at the overhead of 20% or so. But then they can actually reuse also control pin for sending I/O as well. So now they have 16 pins, let's say, that they can use 16 pins for sending packets. And those packets can be data packets or can be control packets. So with that, actually, they potentially kind of widening the shared channel, which reduce the mitigates, how long you need to wait for each conflict. It doesn't solve the conflict problem, but indirectly give us better performance. But actually, in the end, we observed that baseline SSD and packetized SSD do not provide path diversity to flash chips, so you cannot really solve the problem from the source. We also look into some other works, packetized network, which actually from the same paper as the packetized SSD, which they define some vertical channels as well, so horizontal channels and vertical channels. So that can potentially be used to, now you have a little bit more path diversity, okay? So you can use it. Also, there is another prior work, network on SSD, which they use a mesh network to connect flash chips, essentially. But we observe that these packetized network SSD and network on SSD, they do not effectively utilize the path diversity. So it's important that to provide path diversity, but you should also have a technique to utilize that, So that's actually very challenging. And they also incur large area and cost overheads, specifically for network on SSD, because they consider that we have, like, for example, this flash chip is connected to 4 other flash chips, meaning that we actually have more pins, but that we cannot have. So the number of pins is limited. So our goal in this work is to fundamentally address the path conflicts problem in SSDs by increasing the number of paths to each flash chips, providing path diversity at low cost, and effectively utilizing the increased path diversity for communication between the SSD controller and flash chips. With that, we propose Venice. This actually comes at the, this network of channels in Venice, even though I'm seeing kind of a shared channel, which can be potentially bottleneck. We were actually brainstorming a lot before the deadline to which channel we can call it. People discuss about having a Panama canal, Venice canal. And in the end, I think we come up with Venice. And poor Rakesh actually has to redraw all the picture, all the plots, just 1 hour before the deadline. Because we had another name for all this technique and we quoted in in the plots. So he had to generate all of them, 1 hour. So yeah, it was tough. But I like the name, actually. So this actually low-cost interconnection network of flash chips in the SSD and conflict-free path reservation for each I/O request. And we are using a non-minimal, fully adaptive routing algorithm for path identification. I'm going over them relatively quickly, but we still have time. Good. So the architecture actually is that first of all, we define another terminology, which is flash node. And again, we have a network. We have a topology here. We're going to also have a lecture on interconnects. But here, for example, this network, this topology is called mesh, 2D mesh network. So flash node is actually another structure, which is a flash chip connected to a router chip. So that's another. So still, flash chip is actually connected with 8 I/O pins or so to the router chip. And router chips are in the network. So that's one big difference here, because we didn't want to complicate flash chip. Okay. So Venice provides increased path diversity at low cost and no modification to existing flash chips in Venice. So that's with that architecture. And then we wanted to have kind of a path reservation. The main reason here is that since now we have a network, if we just send packets, these packets are read and write commands are actually very large. You know, like think about 16 kilobyte of data, and each link is actually 8 bits. So that 16 kilobytes is going to be huge, right? If you just send it to the network to say, okay, at some point we receive to the destination, there are going to be some other also transfer in between, which at some point they may conflict to each other. So then you have two options. One is to drop, one of them. The other option would be to essentially you have actually 3 options. Drop it, or misroute it. Just when you have a conflict, you just say that, okay, I'm gonna take another path, which potentially I'm kind of misrouting myself, but I'm just gonna take another path. This actually kind of considered in the past as hot potato routing. Like people just pass hot potato to each other, without, no one can take it, because it's a hot potato. And another option would be also to buffer it. The problem is that these packets are relatively large, and if you want to buffer it, you need to add a huge buffer space per router chip. So we didn't want to do that. Also, we didn't want to have this misrouting without control, such that these large packet, like 16 kilobytes of data, just going over and over. That wasn't really good for us. So that's why we come up with this idea of path reservation. It's actually similar to circuit switching. You're going to learn about circuit switching also later in our interconnect lecture. But we send a small packet, which we call it scout packet. And with that, we reserve a conflict-free path from each I/O request. So with this example, we want to target flash 8, for example, here, and we send a scout packet. And this scout packet actually transfers through different routers. And in each router, we have a reservation table. We can reserve packet ID from which entry port and exit port, and then we can say this valid. So essentially, whatever comes from the left port will be exit from the right port. So that's a reservation. That simplifies actually the routing logic as well. So we just do that. And while the scout packet is moving, actually, we also reserving until it gets to the destination. And since all these links are bidirectional, we can actually move back to the flash controller using the reserve path. Here's the animation. So gets to the flash controller, and now flash controller understand that, okay, path is reserved, and we can send the write request, or we can use for the read request, for example. So that's a reserve path. Now when we have another target flash node, we actually pick up another flash controller, like for example FC2, and then we send using another. So now you can see that it's another path, okay, and we reserve it. So path reservation eliminates path conflicts by enabling conflict-free I/O transfer, and also the overhead of path reservation is negligible due to the small size of the scout packet. Scout packet is just like 2 bytes, for example, if you think about it. However, this routing is not enough. There might be some cases like this that you have some active requests to flash chip 6, active requests to flash 8, and active requests to flash 7. Okay, so all these are possible at the same time. However, now you want to also send a request to flash 2, and the only remaining flash controller is actually flash controller 3. So you pick up that, but now you can see that there is no actually minimal pass to that F2. Minimal pass, I mean taking the minimal number of hops to get to the destination. Now here is where actually non-minimal routing algorithm comes to play. So you try to route it in a non-minimal way to the target flash node, F2. And with that, actually, you can increase how much you are benefiting from path diversity. There are a lot more in the paper, which I don't have time to go over, like how we handle deadlock, live-like, many other things and stuff. But yeah, essentially, we evaluate using MQSIM and compare with prior work. And we observe that, so the path conflict-free SSD, which can ideally be built, assuming that each flash node is, each flash chip is connected to the flash controller by isolate channel. So if you have 64 flash chips, you have 64 channels, in an idealized way. So path conflict-free SSD is that you can build up just to get, some room, see how much performance we can get in an ideal way. But with our technique, Venice, actually, we bridge the gap nicely compared to prior work and how much we can get the performance of this path conflict-free SSD. Yeah. And yeah, we also tested over performance optimized and cost optimized SSDs. And basically, we show that Venice is actually very good. And also, we show that Venice reduced the path conflicts very much, a lot, like 99.98% of IO requests do not experience path conflicts anymore. Yeah, it also improves energy consumption. And if you want to learn more, you can also check the paper for more detail. And that's about Venice. Any question? Yes. We don't ensure. Yeah. No, I mean that's a tough procedure in the end. Like whenever you have a network and you want to implement non-minimal routing algorithm, and at each stage, which output you take, you need to really do some congestion awareness technique. You need to know the local congestion, global congestion, and based on that, understand where to go. It actually has been implemented a lot in network on chip. But here in the interconnect of flash chips, we are very much limited on the pins. So for example, we couldn't really come up with a congested network because in some prior work, they move congestion information through a separate network. There is a separate network only to inform all nodes about what's the congestion going on in the network. And that can be used for the routing. But here we wanted to be completely out of that. So that's why it's very simple. And the beauty is that with that simple technique, it actually works really well. So yeah, that's about this lecture. I mean, SSC is actually, and this the line actually is kind of very active research in Safari. We have developed simulator. We are now actually working another version of this simulator. So if you're interested to help, just write me. We have published a lot of interesting work in this line, which I'm kind of flashing them here. You can read these papers if you're interested. Using SSDs for doing computation, like GenStore in a storage-centric computing. Also, when you have different SSDs in a hybrid storage, how you manage the data mapping and migration across these hybrid storage. Doing computation using flat chips in Flash Cosmos paper, this Venice paper that we discussed. Another storage-centric computing for metagenomics. Doing homomorphic encryption using flash memory, cipher match, and Mars, which Konstantina was one of the leader of this work to do for another important genomic application. For retrieval augmented, for example, for LLM. So yeah, there are a lot. So if you're interested, I mean, this line is actually very much active. So just you can just write to me if you're interested to work on this line. And next week, we're going to get to actually details of NAND flash memory, how the characterization, mitigation, and recovery in flash memory. So there are going to be a lot of interesting studies. We have had some similar tools as DRAM Bender for flash memory. So you can actually it's going to be really fun next week. Okay, so with that, I actually went over time for minutes. I'm sorry, but I think it was fun overall. Any burning question? Great. Then I wish you a nice weekend and see you next week.